right, thank you, DK. Let's see. Okay, great. So my name is Paul Narbertil. I am the, and that actually works, cool. I am the Director of Visualization at the Texas Advanced Computing Center, and thank you to DK for inviting me to give this talk today, and thank you to Hari and Matt and Jeff for all your hard work in making sure that we can all be here. So I'm going to talk to you today about visualization communication at scale, meaning how visualization applications are using MPI in very broad terms, and some opportunities that might be available to leverage some of the exciting developments coming out in MPI4 and also further reaching advanced work to target visualization in particular, and in particular on large systems like the machine that we can't talk about, that Dan talked about, that are really going to be using many more cores and some of the implications of that, and how we're actually going to do analysis on the simulations that are being produced. So I'm going to talk to you a little bit about in situ visualization, which means visualizing and analyzing the data coming directly off the simulation without writing the data to disk in between necessarily. And then some general opportunities about how MPI could help aid that process, because it's really in its infancy, in part because folks haven't had to use it. The file system has been good enough, or people have been willing to put up with writing out to the file system and reading back in. But as we get further and further along in interconnect, bandwidth is improving, processors are definitely improving, if not in raw core counts, definitely in terms of the number of processes and the vectorization and just overall parallelization of the system. The file system is just maintaining basically status quo in terms of the IOPS and the bandwidth that it can sustain. And so we have to do something else if our data is growing, but our ability to read that data is staying the same. Then I'm going to go into a short performance analysis study that actually came with one of our partners from the Intel Graphics group that also primarily is officed in Austin, and some issues they ran into trying to get rendering performance distributed across Stampede and the Theta system in Argonne. And then in the negative 5 minutes I'm sure I'll have at the end of that, before our group picture, I'll entertain a question or two. And I'm around through the end of tomorrow, so happy to, and actually I hope that this promotes discussion perhaps at dinner, and unless we're doing another trivia night. Okay, so a little bit about in situ visualization. So as I said, in situ visualization is doing the analysis without necessarily writing the data to disk, and usually while the simulation is currently running. And why do we need to do that? Or actually, let me take a step back. So software-defined visualization is using the same resources to analyze and visualize the machine as are used for the simulation itself. And so in Stampede 2's case, that's using the Skylakes or the KNLs to do the visualization operations and rendering and producing the images, which is the same hardware that the simulation runs. In the past, we were running, we would have dedicated visualizations, either subsystems or dedicated visualization machines. Oftentimes that was just downloading the data to your local desktop or laptop and doing the visualization there, typically leveraging hardware acceleration, having GPUs available. And if you, what we're saying here with software-defined visualization is if you have GPUs, great, use them. If you don't have GPUs, in the past it was, well, you're out of luck. Now we're saying there's a solution to use the hardware that's available and the software techniques that you want to achieve the best analysis outcome. And so basically we're saying that as data sizes grow here, we're well into the terabyte range, and as we're reaching petabyte size of data sets, you never want to move this data off the machine where it was produced. You can get PhDs in the amount of time it would take to move a petabyte over wires, right? You don't want that to happen. And so what this normally looks like is if we have data sitting on a parallel file system, typically Lustre, and certainly in tax case, we have some number of time steps that have been written out to the system, and those can be checkpoints or they can be explicitly written out for analysis. You run the visualization algorithm, which is a filter on turning this data into something that can be rendered by a rendering algorithm, either ray tracing or rasterization. So this could be isosurfacing, this could be doing some sort of volume transform, it could be filtering, subsetting, any number of things to reduce the data into just what you want to be analyzed. And so that then produces geometry or some other renderable that then gets fed to a different algorithm, either ray tracing or rasterization, to produce the pixels that you can either display directly or write out to the file system again if you're producing a movie or if you just want to do analysis later. And it is common in this process to iterate. If you're anything like me or the scientists that I work with, very rarely is your first script the perfect script that you've ever written. You know, if that was true, we would have had if that pitch 1.0 and it would have stopped, right? And so code always goes through this iterative process, and data analysis is the same way, where you might realize after your first image is produced, gee, I need to change this time step. This isn't exactly the right time step that I wanted to see, or maybe the camera needs to be tilted about 15 degrees to the right to really capture that feature, or maybe, gee, this is a point-based data set and I'm not really seeing the feature definition that I would expect it. I'm going to transform it into a gridded data set so that I can use different visualization algorithms. And then once you're done exploring it, you say, now I have this perfect image, now I want to refine it to get that perfect figure for my next proposal or my next paper. And then once that's accepted, you say, wow, I want to refine it even again because this is now going on the cover of Nature or on the cover of Science. And so there's a constant iterative process for any sort of analysis framework. And it's easier to do when you have the constant of this original data sitting on disk, so you just have to fire up another job in the scheduler, get some nodes, and operate on the data. If we take this away, and now we don't have a version of the data on disk that we can readily analyze, now what do we do? And that's where in situ comes in. And why are we moving this way? Because writing and reading to and from the file system is just getting disturbingly similar to the first graph I showed you about transferring the data off of the system. We have larger file sizes here, from terabyte into exabyte. And certainly if we're in the petabyte range, we really don't even on a terabyte per second file system, which is about the capability of our fastest flash-based system at TAC, and I think the Comet at SDSC has similar capabilities. You're still at the check your email, do this over lunch phrase if you need to write out or read in a petabyte of data. And once we get into exabyte, this just isn't going to happen. You know, whole lives go through trying to do this over a gigabit per second. So why is this bad? Why can't we just write fewer time steps and then just analyze the time steps that we are able to write? Well, if we have high frequency writes, we can, and if we're if we have the luxury of writing out every time step, we can analyze at the same, or we have data at the frequency that we want to perform the analysis. And so we can see a nice, even feature evolution, for instance, when we're combining ensemble runs to get hurricane path predictions. And so we can see exactly how these features evolve, and if we need to go back in time and say, well, what happened at this earlier time step? How did we get to the hurricane coming here? I can move back in time and just I oscillate so that I can really understand the evolution. But if I only have the beginning time step and the end time step, I see the problem, but I have no idea how we got there. And so now we need to come up with solutions to how to fill in this middle if we can't write it out all at the same time. So for the in situ visualization generally, this looks very similar to that first chart. Instead of the data being written, now we have the simulation running, and then we have some connection of the simulation and the visualization operations. And unfortunately, this cloud is where all the magic happens. And it is, I was really reminded during the initial talk today, it feels like we're at the 1990 stage of where MPI was in terms of standard development, because there are a number of competing ways that you can fill in this cloud. I'll show you on the next couple of slides. And we need to have a grand unification meeting to really hammer out what is this going to look like in the future. There are initial steps in the community to handle that, but not a unified voice by a long stretch. This is a slide courtesy of Ken Borland at Sandia. There was a 6-month effort by an international body of about 50 visualization and analysis experts across the globe to just come up with these 6 axes and these classifications of in situ types. So it's, I don't know how the origins of MPI went, but I'm hoping that it's that there's hope for us that things move at that pace. But this is a very useful chart that we have 6 different modes of MPI, of in situ access, and then the different classifications of it from implementation type to how carefully or how closely the visualization and simulation processes interact. And some key things here are proximity in terms of how MPI might be able to help. That you might be sharing the same memory on the same node of the system. You might be on the node but with distinct memory spaces. Off node, same computing resource, or in a distinct, on separate resources. And the types of access you have, from shallow copy to indirect access, and the time division. When is the analysis running compared to when the simulation is running, and are they operating synchronously or asynchronously? So one opportunity for MPI to help is operating both in this tightly coupled space where the visualization and simulation are running on the same node, and utilizing buffering to ease the ability for the simulation or for the visualization both to have the ability to iterate in time space and analyze more than a single data step. Now, certainly this requires having sufficient resources on the cluster to stage data in some way, but if there's an opportunity to utilize, for instance, if there's NVRAM, the Intel Optane chips, that might be an interesting layer for this type of caching. If there's a flash system where writes could be staged in a burst buffer, which isn't ideal, but it would be less impactful than writing down to Lustre, or even potentially utilizing hybrid memory if there's a run that is combining both CPU and GPU resources. Could those be combined in some way? And these are already initiatives that we have been talked about earlier today that address this. During DK's talk, the discussing about MVAPICH X, the MVAPICH GDR, that are already dealing with memory questions like this, or potentially solutions that could be directed towards these questions. And then certainly when you're dealing with distinct compute nodes in the same machine, the opportunity to use things like the dynamic and adaptive MPI sensing to when the simulation and the visualization nodes are communicating and how to route that most efficiently. Particularly if there are patterns that emerge during, because there's typically a human in the loop here doing some interactive analysis, that having an adaptive process would greatly benefit, because it's hard to program for what the human might want to do, or might how they might want to guide the analysis. If the visualization analysis is scripted, as sometimes comes later in the analysis process, once you already know what you're looking for and you just want to generate more of the same, then that could be even better opportunity for providing hints for how the process might evolve, because the script will just be iterative and will continue to operate in the same fashion. Further, as oftentimes in exploratory viz, what you're looking for, you don't realize you found something until you can actually see it. I know that sounds a little weird, but basically, once you see that the feature has evolved, you then want to backtrack and understand, okay, how did that come to be? And if you're only dealing with a single time step at a time, you basically have to restart the simulation under the same conditions and rerun it to that point. And if you have it checkpointed in 5 hours, that is not the ideal operation for interactive analysis. So again, this idea of buffering, dealing with a more complex and heterogeneous layers of the memory hierarchy, and if having the ability to efficiently move the data in and out of this hierarchy with adaptation can provide this sort of interactivity to an in situ process. And then a third one that I want to mention is really a rather straightforward one, and I think it was mentioned earlier, is that certainly in the Viz community, everything's two-sided communication. We're fortunately using asynchronous communication. We've at least made it that far. But in terms of what is possible, the communication layer by and large is focused on correctness as opposed to optimizations. And there are other modes that are being looked at in terms of optimizing at the processor level, and we really as a community haven't deeply addressed opportunities at the communication level. And so finding ways to, even within the visualization process, to utilize one-sided communication to more efficiently migrate data around during the analysis could be very beneficial, particularly because interactive visualization has strict time requirements, which I'll talk a little bit more about in the next section. Basically, we consider interactive at around 10 frames a second. So we have about a tenth of a second to do all of the processing of the data to register the next update, be it a camera movement if they're doing a pan or a zoom or a other sort of movement, or to register the rendering of the filter change that's happened. Maybe they changed the color map, so they want a color update. Maybe they moved the transfer function, so they want to see a different isosurface being generated. And so to have that level of interactivity, we really need to start addressing these type of questions as well. This is going to get even more important as we move into more immersive types of environments. So VR goggles, augmented reality, because you need to maintain a higher frame rate in order to make those environments more visually appealing. Typically about 30 hertz is bare minimum, and there are some, like the VR goggles, the Vive and the Oculus Rift, really aren't happy unless you're rendering at about 90 hertz. One of them, I can't remember one of the two, actually won't even display anything if it's not getting the signal at that frequency. So being able to pipe render a massive simulation and pipe the results to a local center in an immersive environment in a goggle space would be an ideal solution, but we'll need a lot of help to get there. And we as a speaking as a visualization person, could definitely learn more about the inner workings of MPI, and we certainly should do that as good software engineers. But there are opportunities here, I think, to create a larger whole out of the contributions that we can all bring in. Okay, so I want to talk a little bit about this performance example, which is specifically doing tiled sword blast rendering. And I'll tell you a little bit more about what that means. This is courtesy of Will Usher, who's an engineering intern at Intel, working with the graphics team under Jim Jeffers. He's also I think he's just finishing his doctorate at the Ski Institute at Utah. And so tiled is exactly what it implies. You have some data set and you have an image of a window, a frame buffer of that data, and you want to render an image of it. And so you divide the image into tiles, and you send these tiles to the process pools, and you just distribute them across. Then they render the data that maps onto their tile, and then they exchange those tiles in order to composite them together in a sort blast method, and I'll tell you what that means in a moment. And then, as a final gather step, all of the various composite tiles are then stitched back together to provide the final image. And ideally, all of this happens in 100th to a 10th of a second. So sort blast means that basically you're dealing with distributed data. And so no one process has a universal view of all the data. And so it takes the tile and it projects it onto the data set that it has and renders what part of that data is visible and in that tile from the process's perspective. It maintains the depth of values so that at the compositing step, all of the tiles that had pieces of that particular data set can then stitch it together, and with the depth value, you can resolve a final image by understanding which parts of the data set were on top. And so this allows us to render data that's much larger than would fit in a single node's memory, but still get a seamless final image. And Ice-T, written by Ken Moreland out at Sandia, is the industry standard in visualization for performing this type of compositing. And so what we're measuring is within the Intel ray tracing engine Osprey, they have a new method of doing this, leveraging some of the facts that it's doing it via ray tracing and leveraging some of the sampling efficiency that the ray tracing engine gets you, and can we do better than what Ice-T provides? So a bit about the configuration setup. Tested on the Stampede 2, both the Skylake and the KNL side, and Argon Theta, which is a KNL machine. I'll say that we used a different MPI stack. And maybe that was the first problem, so we should have been using Babbage, but unfortunately I didn't run these tests, and these were all using Intel MPI. We tested two image-based sizes, 2K squared and 8K squared. And this is getting to the resolution of these immersive environments to be able to provide these types of interactions. Each tile, each work unit is 64 pixels squared, which equates to about an 81 kilobyte payload in an MPI message. As these tiles are being distributed to the various processes, and then the results are being read back. The tiles are distributed point to point, and the partial tiles are gathered point to point among all of the cohort of processes that have a similar overlapping contributions. And then the fully rendered tiles are also sent to the master asynchronously in a point-to-point communication as the tile contribution is completed. Threads will switch from rendering to compositing asynchronously as the rendering work dies down and the compositing work creeps up, and then we're comparing against ICT. And so what we saw on our first runs on KNL is that we start to see this huge spike of performance at 256 nodes. And suddenly, the scaling is not being maintained, and we're actually getting some really bad results here. And 256 is the magic number because that's the size of the normal queue on Stampede. And basically, Will was asking whether he could get access to the large queue to continue to do scaling resource, or to continue to scale out. And our HPC gatekeepers rightly said, well, I'm really concerned by this, so that if you go to 512, the charge is going to be up here. Let's figure out why this is happening before we let you just burn excess compute time. And then on 8K, we see it happens even more quickly. So that suggests that it's something having to do with the amount of traffic that's being generated, since this is generating on the order of 64 times more messages and more data moving around in the system. Then did run on Theta at Argonne, which had a larger normal queue run limit, and this confirms that absolutely we're getting a really bad spike here, and interestingly, ICT isn't. So it's something having to do with the implementation, really within Osprey. And so did a rank-by-rank comparison or analysis of what's happening. This is on 128 nodes at 8K resolution, and we're seeing that every so often one node will just have to wait for almost a full second and a half for all of the remaining incoming traffic to arrive before it can finish processing the compositing work. And unfortunately, there's no rhyme or reason to this. It's not a bad layout on the system. It's not a particular node just getting overloaded with work. It just seems to be consistently that there's these spikes, and it's really degrading the performance. So what's going on? We initially thought that it might be having to do with the eager versus rendezvous implementation of the communication, and so we set the environment variable to increase the eager buffer size just as an experiment, and it helped at smaller resolutions, but at 8K we were still seeing this behavior. And it was the message volume too high, and maybe, but at 8K at 128 nodes, you're only dealing with 128 tiles per process, and so 128 messages per process really doesn't seem that high. But then maybe it's the combination of both the size and the volume, and then we said maybe that's it. That maybe we're just either the work is queuing up, or otherwise we're overloading the buffers even at the larger size, and it's just not having the ability to process it efficiently. Maybe it's just the Intel implementation. I didn't say that, but maybe there's something to do with this combination. So what Will did is he used Google's snappy compression algorithm and compressed both the per tile data down to 2.5K, and the final image composition shrunk from about 270 megabytes down to just 13. So really good compression here, and because of this compression, was able to re-implement the final gather as just an all gather at the end of the render rather than doing the point-to-point composition of the final image. And the cool thing is that this compression worked. And so now in StampD2 KNL, scaling out to 1,000 nodes, ICE-T, interestingly, has a spike, or relative spike. We're still only at 200 milliseconds here, at 128, at 256 out to 1,024. But Osprey is now able to have about 50 millisecond performance out to 1,000 nodes, which is kind of cool. And then that's on KNL at 2K resolution. Skylake we have similar, and you can also see this is a little more jumpy, but this is at 20 milliseconds. And so some of this is just measuring noise in terms of the timing that you're seeing. But out to 256, still getting really nice performance at about under 15 milliseconds. And then on Theta, we were also able to see similar performance out to 1,000 nodes. At 8K, it gets even better comparatively. So ICE-T is still doing a very nice job out to about 8/10 of a second. And Osprey is seeing really nice scaling performance, actually getting faster the more nodes you add to under 200, about 150 milliseconds at 1,000 nodes. And then on Skylake, out to 256 on 8K. And so, again, what we're seeing is that as the work increases by, again, about a factor of 64 here, we're able to really get some nice scaling results. And Theta out to 1,024 and 8K, also similar. And so this is showing that same chart where it's 128 nodes at 8K, and so now all of that jumping has just completely been eliminated. And so just with normal vanilla settings, we're able to stay within those eager limits, and it seems to really work well. And so unfortunately, I'm really interested to hear y'all's reaction to those charts, and if it's, if there's something in terms of understanding how the innards are working that might be causing that, and definitely very eager to rerun these experiments with the Babbage install on StampD2 to understand if we see similar behavior in this case. But definitely, it's as a user of MPI, it's a bit mystifying sometimes to see experiences like this, but it's great that the community is able to provide insights to allow us to get and iterate in a really relatively short amount of time to a workable solution that not only solved the problem, but ended up with a better overall implementation for having gone through it and getting some really nice performance numbers. So with that, I'll thank you and entertain any questions.